Okay, welcome to today's lecture. Before we start today's lecture, can anyone please confirm that you can see my screen and you can hear me clearly? Okay, thank you. Thank you. Okay, so last time we had just introductory lecture and we were talking about the logistics of the course and like what will the grading policy and how many assessment items we had, how many of them will be counted, and so on and so forth, right? So today is our first real lecture, right? So uh, today what we are going to talk about is basically number systems. We will have a couple slides about introduction about the micro. Major part of the slide is about how to represent numbers in different systems, in different representations, and then we will build on today's lecture to talk about how we can represent signed and unsigned numbers later on. Okay, in the upcoming lectures. So uh, the Atmel, whose microcontroller we are going to discuss a study in this course. So the microcontroller which we are going to cover is Atmega328P, right? And here you can see its number, right? Uh, the Atmel AVR, it's not precisely clear what AVR stands for, but some people say that AVR actually stands for the name of the designers of this processor. So these were two students from Norwegian Institute of Technology who designed this microcontroller. Uh, we can consider it as a miniature computer. Remember, in the last lecture, we talked about what a miniature computer is. So by miniature computer, we mean that on a single chip, we have all the components which are needed to perform basic computation. So which means CPU, memory, core memory, data memory, IO peripherals, timers, interrupt unit, and so on, right? So this is the so on this single chip, within the single chip, you have all these components. Definitely, you cannot see them with the naked eye, but they are embedded in the design of this microcontroller. So this microcontroller, it uses Harvard architecture. What does it mean? So we will talk later on in another lecture in more detail about what a Harvard architecture is. But here, let me just state the main the core feature of the Harvard architecture, which is like both the code memory. So there are in the Harvard architecture, what happens is that you have a CPU and then you have two different memories. One memory is used to hold the code, the other memory is used to hold the data. And both memories, they are connected with the CPU with separate buses. So that is Harvard architecture. In contrast to Harvard architecture, we have von Neumann architecture where basically you have a single memory holding both code and data, right? So that is the main feature of Harvard architecture. And this microcontroller is 8-bit. So when we say 8-bit, it's mean that all the microcontrollers are processors, they have internal registers. So registers are nothing but just to hold, but just the data holder. So data can reside in memory, but when the CPU need to access that data, so that data is first placed in the registers. And those registers, why in registers? Because they are very close to the CPU, and it is much faster to access the data for CPU from registers instead of memory. So the size of those registers in this microcontroller is 8-bit. That's why we say that this microcontroller is an 8-bit architecture, 8-bit microcontroller. Like majority of the registers, not all of them, but you can say like 95% of the registers have a size of 8-bit in this microcontroller. Again, this is a RISC microcontroller. So RISC stands for Reduced Instruction Set Computer. At this time point, I'm not going to explain what are the details are the main features of RISC microcontroller or RISC architecture. We will talk about that later on. But because if we talk about risk at this time point, then I will not be able to cover the main content of the slide, which is about different number systems. Okay. So you now have a very brief idea of what a Harvard architecture is. You have a very brief idea of what it means that a microcontroller is 8-bit, and with the details about risk, we are postponing them for now. Okay, so the microcontroller we are going to study is Harvard architecture, and it is an 8-bit microcontroller. By the way, any time point, if you have questions, you can stop me, okay? So the topics we are going to cover are in this slides are number systems, then how we can convert numbers between different systems, number systems. Also, how can we represent a negative number in the binary form, and then we will also have a look at the end a look at the ASCII code. So let's first talk about decimal number system. So in decimal number system, we have 10 distinct digits from 0 to 9, right? So like in terms of like if you have so 0 is the smallest and 9 is the largest digit. So if we want to count onward from 9, what we do is that we simply uh, start repeating the digits. So what we do is that we put 0 in the unit place, and then in the uh, decimal place we put 1, and then we start incrementing the values in the 0 in the unit place. So it becomes 1 0, then 1 1 1 2 1 3 1 4 1 5. So you can see that in the unit place what we are doing is that least significant digit here we are incrementing it, and we keep the next significant digit same, like 1 1 1 1 1 0 1 1 1 2 up to 1 5. So once we will reach at 1 9, what we will do simply we will increment the digit in the decimal place from 1 to 2, and then we set the digit in the unit place to 0. So it will become 2 0 or 20, and then 2 1 2 2 and so on, right? I mean, everyone is familiar with that, right? Everyone knows how we can count, right? So now if we talk about the hexadecimal system, so in hexadecimal system, unlike decimal system, we have 16 distinct digits. 0 to 9, they are same as the decimal system, as in the decimal system, but then we have the digit A, B, C, D, E, and F. So A is basically used to represent 10, and B is used to represent 11, and so on, and F is used to represent 15. But these are distinct digits. So we have like in total we have 16 distinct digits from 0 to F. Okay, let me just give me 1 minute. Hide floating meeting controls. Okay, let me not hide them because then. Okay. Now let's have a look at the octal number system. So in octal number system, we have 8 distinct digits, and they range from 0 to 7, right? So after that, what happens? Same exactly as we saw in the decimal system. What we do is that once we reach the maximum value of a digit, then we set the unit value to 0 and increment the value at the decimal place, right? But the maximum value we can have any and in any place is 7, right? So we have 1 0 1 1 1 2 up to 1 6 1 7, and at this time point of the next number after 1 7 in octal system will be what? It will be 2 0, right? Because we will increment the digit in the like second in the most significant place, so it will become 2, and we'll replace 0 with 7 with 0, right? Okay, now let's talk about binary. So in binary, we have only 2 digits, 0 and 1, right? So for example, if we use 4-bit binary, so all bits will be 0. Then if we increment it, so these 3 bits will remain 0, and the least significant bit will be incremented by 1. Now we have reached the maximum limit, right? Because we have only 2 digits in the in the binary system. So what we will do is that we will increment that digit in the next bit position, and set the digit in the least significant position to 0. And then we increment the bit in the least significant position and keep this one same. Now again, we have reached at the maximum value. So what we will do is that we can now increment this one, right? Because it is already maximum value. So we'll simply increment the next bit and then set both of them to 0 and so on. So it will be 100, 101, 110, and so on. I guess you guys got the idea of the pattern, right? Any question at this time point? No? Okay. Okay. So number representation in AVR. So we have seen that we have seen four different number systems: decimal, octal, binary, and hexadecimal, right? So how can we represent all these numbers in all these four number systems when we're writing a program or assembly program in the assembly program for an AVR microcontroller? So when we are specifying numbers in the program, we can specify whether that number is a binary number or an octal number or hexadecimal or decimal number. So how we specify? So to specify that the number we are writing is a binary number, you can put a leading 0b in front of it. So if you put 0b in front of it, so the assembler will treat it as a binary number, right? Uh, to specify a number in the octal number system, so you need to place a leading 0, only 0. So if you place 076, so the assembler will understand that this number is in uh, octal number system. In decimal system, the leading digit cannot be 0 except when the value is 0. So in decimal system, you don't need to put anything in the leading position. So if it is 62, you will write 62. You cannot write 062, because if you write 062, then you will be expecting that you have written the number in the decimal form, but assembler will interpret it as a uh, octal number. So the actual value will be different according to your interpretation and according to what assembler is understanding, right? And how to specify a number in hexadecimal form? For that, you can put a leading 0x. So for example, if you put 0x4f2a, so now assembler will understand that this is a number in hexadecimal form. Okay. Any questions about how we can specify the representation of binary, octal, decimal, hexadecimal numbers in assembly? No? Okay. So how can we convert, when I say convert to decimal numbers, this means that they are in some other system, like let's say they are in the binary form or they are in the octal form or hexadecimal form, and we want to convert those number into decimal numbers. So how can we do that? So let's first talk about how we convert a decimal number to decimal form. So it is already in decimal form, but we just for our understanding, we want to do this exercise, right? So let's say we have 25 and it is in decimal form. So we are writing the base in as like next to the number in subscript, right? So to convert into the decimal back, what you do is basically that you multiply the first digit of the number, starting from the right side. So which let me name is the least significant digit. So you multiply the least significant digit of the number with the 10 raised to power 0, right? And then add it to what? To So what you do is that you multiply the next number, the on the when you move from right to left, you multiply it with the increasing power of 10. So you multiply 2 raised to power 10, 2 into 10, and then you get the sum of both, like sum of products, right? 2 times 10 plus 5 times 10, 10 raised to power 0. So we know 10 raised to power 0 is 1, right? So what you will get, 20 plus 5, which is 25, right? So what is the idea basically here? The idea is that you start moving from right to left, you take one digit at a time, and then you keep multiplying those digits with increasing power of the base of the number system. So in this case, the base is 10. So we are increasing the power of base, like 10 raised to power 0, then 10 raised to power 1. And if there was another digit, let's say it was 325. So here what you will put is like 3 times 10 raised to power 2 plus, right? Plus all of this, right? Okay. So following the same pattern, what we can do is that we can convert the binary number to the decimal form, right? So let's say we have this binary number now, 1011 to the base 2. So here in the subscript, we have the base. So it is telling us that this number is in the binary form, right? So if we want to convert into the decimal, we follow the same approach. So we'll get the first digit, which is 1 here, and multiply it with uh, base to the power 0. So the base is 2. So 1 time 2 raised to power 2 raised to power 0. We multiply the next digit, which is 1, with 2 raised to power 1. We multiply the third number from the when we start from right to left. So third digit, which is 0, we multiply with 2 raised to power 2. So if you notice, we are incrementing the power of the base, right? 2 raised to power 0, 2 raised to power 1, 2 raised to power 2. And then we multiply the last most significant bit with the power of 2 raised to power 3. And then we take sum of all these products, right? So when you will take the products, so it will be what? This will be 8, right? This will be 0 because you are multiplying with 0. This will be 2, and this will be 1, right? So which is equal to 11 in decimal system. Okay. Let me get rid of these annotations. Okay. Okay. So now let's have a look at how we can convert a number which is in the octal system or an octal representation to the decimal form, right? So here we have 76, and its base is 8, which means it is number represented in octal number system. So again, we will do exactly the same thing. We will take 6 and multiply it with 8 raised to power 0. We'll take 7 and multiply with 8 raised to power 1, and then we'll take sum of the two products. So this will be 6, right? And this will be 56. So 56 plus 6 will be 62, okay, in decimal form. This is actually a similar thing which we have already done. The difference is that we are now assuming, or we are saying that 76 is a decimal number. So we want to convert it from decimal to decimal. So it is again the same example like this one, similar example like this one. So 10 raised to power 0 times 6 plus 10 raised to power 1 times 7. So when you will do the math, you will get 76. Okay. Now, uh, the last conversion, which is about converting a number from hexadecimal form to the decimal form. Now remember, in the hexadecimal form or in hexadecimal system, we have 16 as the base, right? So if we have number A5, so what we'll do is that we will multiply 5 by 16 raised to power 0 plus, now A is basically 10, right? Say A10 represents 10 in the decimal form, right? So we are saying 10 times 16 raised to power 1. Now when you will do the math, you will find 165. Okay. So you can basically you can look here. So A is 10. Okay, so uh, I wanted to do the polls, but I didn't have enough time to create the poll. So, but for now, I'm giving you a small exercise to do on your notebooks. I'm writing it in the chat box, and you can do it on for your practice. So convert Okay. Yeah. Convert F503 to decimal form. So F503 is hexadecimal number. So convert it into the decimal form. So I can give you like 2 minutes. 2 minutes are enough, guys, I guess, right? So you can do it in 2 minutes. In the meantime, I can also do the same thing so that we can tally our answers. Okay. So once you are done, let me know. You can write in the chat box if you're done. Okay, thank you. Thank you for letting me know. Okay. Okay. Now let's do another small exercise. Uh, yeah, it is 62723. Thank you. Thank you, everyone. Now let's move to the next exercise. So this time, convert octal number 52312 to decimal form. Oh, sorry. I should have sent it to everyone, not only to 1% person. Yeah. Convert octal number 5231 to decimal form. And you have 1 minute, I guess, because 2 minutes is too much. Thank you. If you are facing any problem or you think you can't do it, let me know, okay? Are we going over the problems together? You want me to do that? If you want me, I can do it on the slides. I thought this was an in-person class and was having issues set up everything right now to catch up. Uh, yeah, sorry for that. It's hybrid, but the video will be recorded and you can watch it later. I will share the link. Gavin, do you want me to go over the problems on the screen? Okay. Yeah, yeah. Let's do the last one, right? Which was converting 5231 uh, in the octal form. Okay, so for that, I can actually go to OneNote and yeah, so the number which we wanted to convert is sorry, 5231, right? And it is a number in octal form, and we want to convert it from the decimal form. So how we can do it? We uh, let me complete this and then I will check the message. So we can take the first number, 1, here, and multiply it with 8 raised to power 0, plus this next number, we start from right and we keep moving toward left, 3 times 8 raised to power 1, plus then the next number on the left side, 2 raised to power 2 into 8 raised to power 2, plus next one which is 5 into 8 raised to power 3, right? So this is 1. 3 times 8 is 24. So 8 square is 64, and 64 times 2 is 128, right? And when you do this math, cube of 8 times 5, so you will get 2560. So now when you will add all of them, you will get 2713 in decimal form. Okay. So this subscript shows that base of the number system. Okay. Uh, Yeah, for octal, we will always multiply by 8. Why? Because 8 is the base of the octal number system. We always, when you are converting, when you are converting from octal to decimal, so because you are converting from octal, so we'll use the base of the octal system, which is 8. When you are converting from binary to decimal, so base of the binary is 2. So we'll always multiply with increasing power of 2, right? Like 2 raised power 0, 2 raised power 1, 2 raised power 2, 2 raised power 3 as we move from right to left, right? And similarly, let's say if you are converting from hexadecimal system to the decimal, so the base of the hexadecimal is 16. So what we will do is that we will always multiply digits in increasing power of 16. Okay. Hope it helps. For test, will we be allowed a scientific calculator? Will be expected to find the powers. You will be allowed to use the standard calculator, not the scientific one. Okay. So with this, let me move on, right? If is there any other question? Any confusion? So silence means no question, right? So I'm moving on. Okay. So decimal to binary numbers. So we have seen in the previous slide how we can convert numbers from other number systems to the decimal form, like from binary to decimal, octal to decimal, hexadecimal to decimal, right? Now we will talk about how we can convert numbers which are in the decimal form to the binary form or to the binary system, right? So first, keep in mind that in decimal number system, we have 10 figures or 10 digits from 0 to 9, right? In binary number system, we have only two digits or two figures, 0 and 1, right? So how we convert a decimal number to the binary form by using the repeated division. What is repeated division? Let me show you. So suppose, let me show you to use an example. Suppose we want to convert 25, which is a number in decimal form. We want to convert it to the binary form. So if it is in the binary form, we can, after conversion, it should have only zeros and ones, nothing else. Okay. So for that, what you will do is that first you divide 25 by 2. Why by 2? Because we are converting to binary form, right? And the base of the binary is 2. So we divide 25 by 2. Let me use the pointer. So we divide 25 by 2 and we write down the quotient and the remainder, right? So quotient is what? 12 and remainder will be 1, right? So what we will do is that we will repeatedly divide the quotient again with 2 until we finally get a quotient value of 0. So for example, we divide 12 again by 2. So when you divide it by 2, you will get quotient of 6, right? And remainder will be 0, right? But is quotient 0? No. If not, so divide it again by 2. So you divide 6 again by 2, so you get quotient value of 3 and remainder is 0. So is quotient 0? No. So divide it again by 2. So 3 by 2, so you get a quotient of 1 and you get a remainder of 1. So again, ask the question, is quotient 0? No. So divide 1 by 2 again. So when you divide 1 by 2, so you get the quotient of 0 and remainder of 1, right? So now here in the first column, you have all the quotient values, and in the second column, you have all the remainder values. So to make the binary form, what you do is that you write these remainder values these remainders in upside down up in upward direction. So the last remainder is most significant bit and the first remainder is the least significant bit. So how you write it? 1 1 0 0 1. So this is most significant bit and this is least significant bit. So you write in this direction. Okay, in this direction. 1 1 0 0 1. Starting from left side. I'm just starting from, like, I'm writing from left to right. 1 1 0 0 1. Okay. Is it clear or not? If not clear, feel free to ask questions. Okay, thank you. Okay, so then let's do this exercise. Convert 352 to binary form. Like, I mean, I can give you like 3 minutes. Okay, so convert 352 to binary form. How you can do that? Using repeated division. So try it on your notebooks. Let me also do in the meantime. Same thing. You can share your answers, or at least tell me that you are done if you're confident your answer is correct by sending a message. Thank you. Okay. So let me show you the answer, and if the answer you found is different from what I'm going to show, then let me know, okay? Uh, so answer is 10110, and then four zeros on the rightmost side, right? How we found this? So you divide 352 by 2, you get a quotient of 176, remainder of 0. Quotient is not 0, so we divide it again by 2, we get 88 as quotient, remainder is 0. Again divide by 2, 44, 0. Again divide 44 by 2, you get 22, and quotient remainder is 0. Divide 22 by 2, you get 11, remainder is 0. You again divide, so quotient is 5 and remainder is 1. So still quotient is not 0, so we continue. Divide 5 by 2, you get quotient of 2, remainder of 1. Again divide by 2, you get quotient of 1, remainder of 0. And then when we divide 1 with 2, so quotient is 0 and remainder is 1. Now what you can do is that you simply write these uh, remainders in upward direction. So this one becomes most significant bit here, right? And this 0 becomes least significant bit here. So by most significant is the bit, we mean the bit which has the highest value. Highest value in the sense that it will have, if we convert it into the decimal form, so it will be multiplied with the highest value of highest power of 2, right? Because this bit will be multiplied with power of 2 raised to power 0, right? And then this will be multiplied with 1, 2, 3, 4, 5, 6, 7, 8. So this will be multiplied with 1 into 2 raised power 8. So since the power of 2 uh, is highest for this bit, that's why we're naming it as most significant. And the power of 2 is 0 for the bit on the extreme right side. That's why we name it as least significant bit. Okay. Any confusion? No? Okay. If no question or confusion, then let's continue. Now, let's see how we can convert binary to decimal form. Previously, we saw how we can convert decimal to binary form. And at this time, we are again, actually, we have seen this example already, or how to convert binary to decimal. So let's go through another example again. So before we talk about how to convert binary to decimal, let's first talk about how to convert decimal to decimal, right? So we have already seen the example. So if the number is 740740683 and the base is 10, so how you convert, so it's mean this number is in decimal form, right? So how you convert it in the decimal form? It is straightforward. What you do is 10 raised power 0. So you multiply 3 with 10 raised power 0. You multiply the next digit on the left side with increasing power of 10, which is becomes 10 raised power 1, 6 with 10 raised power 2, 0, 10 raised power 3, and so on, right? So then you get all the products, and then you get the sum of all the products. So when you will sum them, you will get this number, which is same as the original number, right? Now, how to convert from binary to decimal, right? So we use the exact similar approach. The only difference is that the base of the number is 2, not 10. So what we do is that we multiply the first digit from the right side with 2 raised power 0, right? Next digit with z, which is 0, with 2 raised power 1, and so on. So we multiply all of them, right? And then we take the product, right? So 1 time 1, 0 times 2, so it becomes 1, 0, 4, 0, 16, 32, right? And when you take the sum, it will be 53, right? Now the interesting thing is, so like there are two ways. either if you convert 53 into the binary form, how you can do it, for example, using the repeated division. If you use the repeated division, you will find this number, this binary form. Okay, let's do it on your notebooks. Use the repeated division to convert 53, which is a decimal number, into the binary form. And then I will explain the next thing. I just want you to verify that you will get this binary number. So let me know when you are done. Convert 53, which is a decimal number, into the binary form using repeated division. Thank you. Okay. Okay. So you found exactly this number, right? You got 11010. Yeah. Okay. Yes. Good. Good. So now the interesting thing is, like, if you convert individually all of these products individually into the binary form, like, what is the binary of one? It is one. What is binary of zero? Zero, zero. Like 2-bit binary, right? So here you have 1-bit binary, 2-bit binary, 3-bit binary, and so on. So binary of one is one, zero is zero, four is 100, 4-bit binary of the next digit, four zeros, binary of 16, it will be this one, binary of 32, it will be this one. And after that, if you sum all these binary numbers, so you will also get exactly the same thing, this one, right? Now, we have not talked about how to add together two binary numbers, uh, but I mean, in this case, it's simple and straightforward because it is here we don't have carries, so it doesn't make any uh, it is not a difficult case, a difficult example. So 1 plus all zeros is 1. All zeros is 0. Then in the third column, you have 1 and 3 zeros, so it becomes 1 when you add them together. In fourth column, you have 3 zeros, so sum is 0. In fifth column, you have 1 and 0, so it becomes 1. And in sixth column, you have only 1. So you get exactly the same binary number. Okay. But I mean, this is like kind of, I mean, I would not prefer this approach where you are first getting the binary form of each one of the product individually and then summing together the binary numbers. I would not prefer that because I think to me it is more difficult or cumbersome. I can directly use the repeated division to convert. Okay. So we have seen in we have seen previously how we can convert uh, binary numbers to the decimal form, right? So another ways what we can do is that you can convert binary number to decimal by using another slightly different approach. So what you do is, for example, let me try to explain using the example. So let's say we want to convert this binary number to the decimal form. So simply you first write the numbers, all the digit of the number 11001, right? And then you write the weights. What are the weights? Weights are like increasing power of 2, right? So increasing 2 raised to power 0 is what? 1. So let me actually show it. So 2 raised to power 0 is what? 1. 2 raised to power 1 is 2. 2 raised to power 2 is 4. 2 raised to power 3 is 8. 2 raised to power 4 is 16. So 1, 2, 4, 8, 16. So first I write all the digits in the binary number. Then I write the weights, increasing weight 1, 2, 4, 8, 16, 32, 64, 120, and so on. And then what I will do is that I will simply keep only those numbers for which bit value is not zero. If the bit value is zero, I will simply write the zero. So here it will become 16, 8. So this will be 4. Sorry, this will be 0. This will be 0. This will be 1. So what you will do, 16 plus 16 plus 8 plus 1. So when you will do the sum, it will be 25. Okay. I mean, it is just a different way of looking at the same thing, right? So instead of saying like we are multiplying with increasing power of 2, we are simply saying we are writing down the weights, and weights are like increasing power of 2 again, 1, 2, 4, 8, 16, and so on. And then we sum all those weights for whom the corresponding bit values are not zeros. Okay. Now, let's say we want to convert. Is everyone clear on this one? Okay, thank you. Okay. So if you are like confused, let me know, okay? I don't want to rush. Okay. Next example is how to convert a decimal number to the binary form using the same approach of using weights, right? So let's say we want to convert 39, which is a number in decimal form, to the binary form, right? So what you need to do is that first write the weight up to the point where you get a weight which is like uh, which is smaller than your number. So what is our number which we want to convert? 39. So we wrote all the weight 1, 2, 4, 8, 16, 32, but we stopped at 32. We didn't go to the next one, which is next one is what? 64. Why? Because 64 is greater than 39, right? So again, I mean, I will never recommend you to use this number, but to use this approach. But I just wanted to show that okay, you can also follow this approach to do the conversion. But otherwise, I mean, I would not prefer it because it is like kind of confusing, right? Kind of like more involved as compared to where you do the repeated division, right? To convert a decimal number to the binary form. So let's go back to example. You have 39, so you write the weights until you read the weight which is like largest weight which is smaller than your number. So you reach at 32. Now, what you do is like uh, you want what you do is that you keep the 32 because it is the closest weight to 39, right? So then 39 minus 32 is what? 39 minus 32 is 7, right? So the number which is left, let me write it here, 39, and then I kept this weight. So 39 minus 32 is 7, right? Now I will again look at the weights, and I will try to find a weight which is less than 7, but like largest weight which is less than 7, right? Less than or equal to 7. So the largest weight which is less than or equal to 7 is 4. So I keep 4, right? So now 7 minus 4 is 3. Now again, I will look at the weight which are largest weight which is less than or equal to 3. So that is 2. I keep 2, right? So now I do 3 minus 2. So I am like left with 1. So I look at the weight which is largest weight which is equal to or less than 1. So which is weight value of 1, right? Now it means I need to keep only these weights 32, 4, 2, and 1. So to convert to the binary, what I can do is like I can write here 1, I can write here 1, I can write here 1. I don't need this weight 8, so I put 0. I don't need this weight 16, I put 0 here. I need this weight 32, so it becomes right 1. So the binary form will be 1 0 0 1 1 1. Okay. Any questions? I'm not going to ask you on the exam or in the test this kind of conversion because this is just like uh, crazy. I mean, you can use the simple repeated division to convert to the binary form. Okay. Uh, Conversion between binary and hexadecimal numbers, right? So previously we saw conversion between like binary and binary and decimal and decimal, from binary to decimal and decimal to binary, and now conversion between binary and hexadecimal, right? So in hexadecimal we have 16 digits 0 to F, right? So let's say we want to represent binary number, this bit pattern, and here too means that it is a binary number we want to represent in hex. So it is much easy as compared to converting a binary number into the decimal. Why? What we do is that we group the bits, are binary digits. So binary digit is also known as a bit. So we group the bits into the group of four. So first we group these first four bits 0 1 0 1. Then we write the next four bits in a group of four, which is four ones 1 1 1. And then these one, right? And then we are left with only one bit. So we write one here. But since we need a group of four, so we append four leading zeros here. Okay. Now you can convert this one into the binary form. So when you will convert this 4-bit pattern into the binary form, it will be what? 5. How you can convert? You can like use the weights, like you can say what will be the weight of what, like, do you want me to do that? Okay, let me do it quickly. 1 into 2 raised power 0 plus, I can directly write 0 for this one because the bit value is 0, plus 1 into 2 raised power 2. So this will become 4. This is 0 plus this will become 1, 5, right? 4 plus 1, 5. In the same way, can convert this one into the into the decimal form. So when you will convert, it will be 15. And how we represent 15 in hexadecimal form? Using F, that figure F or digit F, right? And this bit pattern 0001 is equal to 1, right? So the hexadecimal form will be 15F16. 16 is like we are indicating the base of the number, right? So keep in mind what you do is that you simply group the bits in group of four, write down them in groups of four, and then convert each 4-bit group into the equivalent hexadecimal form as hexadecimal digit, and then you write the hexadecimal digits together and it becomes the hexadecimal number. Okay. Okay. So any question? Okay, if you don't have a question, let's do an exercise then. I'm writing it in the chat box for everyone. Convert binary number. And you have 2 minutes. Okay, thank you. Let's wait for a couple of more people to complete. Thank you. Nice. Okay, good. Good. So the hexadecimal number I found is 2D76 is hexadecimal number. Okay. So if you have a different one, let me know. Okay. Or if you don't understand how I got 2D76, let me know. Okay. Okay. Now let's do the reverse conversion, which is converting a hexadecimal number to the binary form, right? So the hexadecimal number that we want to convert is 29B, 29B, right? So for that, what we can do is, I mean, it is straightforward. You know it, right? Using the increasing power of base, and base is what? 16. Oh, sorry. We need to convert it into the binary, not into the decimal form. So what we can do is that we actually do exact reverse of what we did here, right? So what we do is that we write the 4-bit binary of each of the digit in the hexadecimal form. So for example, for B, we write the binary value of B. So what is B in decimal? What is B? Right? I mean, when you will do practice, it will like you will not need to do repeated division anymore. So it will like become handy, and you will like you can quickly tell out, okay, it is 1011. Okay, let me complete it, then I will check the message. The next number is 9. So you write the 4-bit binary of 9, which is 1001. And the next digit is 2. So you write the 4-bit binary of 2, which is 0010. And then you simply combine them. So from right to left. So it becomes this number, right? And in the final version, you can drop the leading two zeros because they have no value, no significance, right? So it will become this number. Okay, what was the question? Oh, there was some message, but okay. So let's do an exercise then to make sure that you understand this, okay? So let me give you a number. Convert hexadecimal number CF 742 binary form. And you have 2 minutes. Let's say 1.5 minute. For the letters, is there a way for use for us to know the value of them? Or are we just going to have to memorize the yeah, you can I mean over the time they will settle in your mind, but for now if you don't remember them, what you can do is that you can do the repeated division. For example, if you want to know the value of the A, right? So what is A? A is 10, right? So you can do the repeated division over 10 to convert it into the binary form to get a 4-bit binary of 10. Do you understand or not? If not, I will explain. Let everyone complete this, then I will explain, okay? On the screen. Okay, okay. I will explain. Yeah, 110 triple 10110 1. Yeah, that is correct, Nicholas. Mm. Okay. Yeah. So uh let me so the correct answer is actually let me show you how we can calculate it, and then I can also in the mean in this when doing that I can explain it to Gavin what he was asking, right? So let me let me go to OneNote. Okay. By the way, I have shared the link of this OneNote page on the Canvas syllabus page of our Canvas course. So you can later on, if you want, you can access it. And it is recorded also anyway. So okay, what was the number which we wanted to convert was CF74, right? So now let me first do it quickly, and then I will explain how to find the 4-bit binary if you haven't memorized it, right? So 4 is like 0010, right? 7 is 1, 4-bit binary of 7 is 0111. 4-bit binary of F is 111, 4 ones, and 4-bit binary of C, which is 12, is 00110, right? So this is how this is the like answer now to the question asked by Gavin. So let's say I want to convert character C to the bit pattern, right? Now I first need to know what is the equivalent value of character C in the decimal system. So C is basically 12, right? So then what I will do the repeated division on uh, 12. I will repeatedly divide it with 2. So when I divide 12 by 2, so 6 is quotient, remainder is 0. Then quotient is not 0, so I can do uh, again, I do the division. 2, so I get the quotient 3, remainder 0. Then I divide it again by 2, so quotient is 1, remainder is 1. So quotient is still not 0, so I divide it again. So this time quotient is 0, remainder is 1. And now to get the binary of 12, I write these remainders in the upward direction. These are the remainders, right? So when I write them from like this is the most significant bit. So it becomes 1, 1, 0, 0. So this is bit pattern for character C, which I have written here, right? In the same way, you can also get the bit pattern for F. So first you need to know what is the equivalent decimal form of F. What number is represented in decimal form? It is 15. So when you do the repeated division by 2 over 15, you will get 4-bit, this 4-bit pattern, 4 ones. Okay. Where did the 12 come from? Sorry. Okay. Yeah. Okay. Let me show you. Here. This is hexadecimal, right? Hey, sorry. This is hexadecimal system, right? Why I can't select the pointer? Let me select the pointer. So this is hexadecimal system, right? And we have the digits 0 to F. And here we have C, right? So C is what? C is equal to 12. Because after 9, we say A. So A is basically what in decimal form? 10. Because in decimal system, after 9, you have 10. But we represent 10 by A. And then after 10, we have 11. But we represent 11 by B. And after 11, you have 12, and we represent 12 by C and so on. Okay. Oh, okay. You're welcome. Okay, so where were we? Okay, is everyone clear on this? Okay, we still have like 8, 9 minutes. Let's use them. So conversion from decimal to hexadecimal form, right? So how you convert a number which is in decimal form to the hexadecimal form. So there are two options. First is that you convert that decimal number first to the binary form, right? You have two steps. In first step, you convert the number from decimal to the binary form, and then you convert from binary form to the hex. We already know how to convert a number from decimal to the binary form, and we also already know how to convert a number from binary form to the hexadecimal form. So we do these two steps and we get the number, right? So here is example. Convert 629 to the hexadecimal form, right? So what you do, you first convert 629 in the binary form, right? So when you will convert 629, uh, let's not look at this table because it is kind of confusing. So let's every one of you, I want every one of you to convert 629 into the binary form. Do it on your notebooks. Convert 629 to the binary form. I'm also doing the same thing. So only convert to 629 to hex and let me know that what binary you found. Okay, if you are done, also please paste write your binary in the chat box. Uh, so we have two steps. We are only doing first step. Matt, you have a question, right? So we are doing only first step. In first step, you are converting the number, decimal number to binary form. Only convert to binary form. 100110101. Yeah, Daniel, you have right answer. Piper, your answer is not correct. Double check it. Yeah, Sebastian, your answer is correct. Zach correct. Max correct. Kodia correct. Uh, no, Brock, you need to double check. Brock pattern. Okay. So okay, let me do it on the screen, right? For those of you who are like getting incorrect binary form, right? So what was the number? Number was 629, right? I'm writing here 629, right? So I divided by 2. So, sorry. And 2, 1 and 2, 4. And you get bind remainder of 1. And 157. And you get remainder of 0, right? 278 and remainder of 1. 239 and remainder of 0. And 219 and remainder of 1. And 29 and remainder of 1. And 24 and remainder of 1. And 2 2 and remainder of 0. And 2 1 and remainder of 0. And if I do it once more, so 2 0 and remainder of 1. Now I simply write it in the upward direction. So this is most significant bit and this is least significant bit, right? So when I convert it, when I write it down, so I get 1 0 0 1 1 1 0 1 0 1, right? And then I group them in the groups of 4-bit, right? And I'm putting comma as a separator, right? So I will get 1 0 0 triple 1 0 1 0 1, right? So this is the first step, right? This was step 1. So where we converted our decimal number into the equivalent binary. But we need group of 4, right? So I am adding only 2 zeros here, right? So now what is the I convert only this group of 4 into the hexadecimal form, right? How I can convert it? You already know by repeatedly multiplying with increasing power of 2. So what it will become? It will be, I mean, I know it, so I can directly write it. It will be 5. This is 7, and this will be 2, right? So it will become in hexadecimal form. It will be 27510. Is everyone clear on this? Do you know how what I did is, again, I simply group the bits in group of 4, right? And then for each hexadecimal form, right? So which is 5, right? And 0 1 1, it is 7, and 0 0 1 0 is 2, right? Actually, what you can do is, like for example, is everyone clear on this before I make it more complicated, or I change the example? Yes, yes, okay, thank you. So now, yeah, thank you. Now, for example, let's say that this our second group of 4-bit was not 0 1 1 1. It was, let's say, I'm just making up something, 1 1 1. So you can basically, what you can do is you can convert into the decimal form. So when you convert in decimal form, it will be 15. But remember, we are converting to hexadecimal. So in how we represent 15 in hexadecimal form, using F, right? So it will become 2F5. Okay. Any questions? Okay. If no questions, then you missed the last part. Okay. Show me again. Let me show you again. Where is it? Yeah. So did you miss this part where I was saying that just assume, let's say this bit was not 0 and it was 1, right? I replaced this bit with 1. Are you talking about this part? Yeah, okay. So if I do that, so what is the like bit pattern for the second group? It is 1 1 1 1, right? So simply convert it into the Decimal form. I mean, if you have practiced enough, you will readily identify that all four ones is F. But if you have not yet practiced enough and you are struggling with that, you can simply first convert into the decimal form. So when you will convert it, you know how to convert in decimal form. So when you convert it, it will be 15. But our target is hexadecimal. So how we represent 15 in hexadecimal form? By writing F, right? So if all other bits are same, I only change the single bit. So the new number will be in hexadecimal form will be 2F5. I missed the last part. Okay. Did you get it, Brock? Okay. How did you go from decimal to X? Okay. Uh, you want me to explain the step two, Gavin? Gavin, do you want me to explain step two? Just how to start it, please. No, I mean, I'm not clear what you are asking about. Are you asking me to start from the step one or from the step two? Start step two. Sorry. Okay. Yeah. So I'm assuming you are clear on, you are understood how I got the binary, right? So I'm simply writing the binary again for like doing it again. So I'm writing the binary like from writing from most significant bit one and writing upward 1 0 0 1 1 0 1. So after getting the binary, I group them in group of 4 bits. Sorry. So 4 bits, 4 bits, and I also add only two zeros here, right? Now I simply convert it into the hexadecimal form. How can I convert hexadecimal form? Again, because you are just starting this course, so you are not able to readily identify what is the equivalent decimal form of this 0 1 0 1. So for that, if you don't know, you can simply go to this table, back to this table. So what was our bit pattern? 0 1 0 1. In hexadecimal form, it is what? 5, right? So you can simply write 5 here. Again, for the next bit pattern 0 1 1 1, you can again look from the table and you will find it is 7. For the next bit pattern, you can again look in the table and you find that in the hexadecimal form it is equal to 2. So the number in hexadecimal form will be 275 to the base 16. Okay. By the way, here I guess I made mistake. It should be 16. Sorry. Okay. Is it clear now? Just how to start. Okay. 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 You're welcome. Okay. So any other questions? Any comments? No? For the lab, are we going to need the kits? Yes, as I mentioned in the first lecture, you need the kits. So either you can buy from Amazon or you can contact the students of the like last offering of the course. They had the kits, maybe they don't need them anymore, and you can ask them, you can borrow from them or you can buy from them. What if our kits are delayed from the storm? Uh, Okay, make sure that you have purchased the order. Oh, sorry, you have placed the order. If it is not arrived by that time and they are delayed, then I can give you extension for first lab. I will receive mine Friday. Okay, so when we have our first lab, let me check the syllabus. So the first lab is due on Feb 2, right? So you have time. It will hopefully arrive. So the lab will be released on 28th, but it is due on, here you can look at my pointer. It will be due on 4th Feb. Uh, yeah, so you will have the time. Again, I answered this question last time. Like, is there lab today? You can readily answer yourself by just asking, is the lab due today? if the lab is due today and you are still not done with the lab work, go to the lab and do your lab work and show to the TA. But let's say if the lab is not due today and you want to work on your lab like in advance, so the lab is still reserved for you. You can go there and you can do your lab work. Did I answer your question, Gavin? I should know. I emailed you first day that I wasn't here. Uh, yeah, watch the video of the first day. I have placed the link here in the syllabus document. So you have YouTube link of the video. Go and watch it and so that you get all the information. Okay, you're welcome. Will this recording be available? Yes. I mean, I will place the video on YouTube and share the link on Canvas. Okay, you're welcome. Okay, I think that's it, right? So have a nice day and see you on Wednesday.